In today's lecture, we will continue with structural mechanics. Let us recapitulate what we have already learnt about structural mechanics. In the first case, we analyzed trusses, which consists of members which are two force members, that is, the forces are applied at only 2 points along the member, and as such there were only tensile or compressive forces in each of the member of a truss. The second type of structure which we started discussing last time was a beam. Beam is meant to take up transverse loads, forces as well as moments in the plane of the beam. Now, even if there is an oblique load, we can decompose that load into a transverse component and an axial component. The axial component will produce, according to its direction, either tension or compression along the beam, whereas transverse component produces two types of reactions. One is the shear force, the other is the bending moment. This we have seen from consideration of equilibrium. Now, towards the end of last lecture, we also studied the properties of a section. Whenever a beam is cut into by a plane section, the two surfaces so produced, one of them is a positive surface, the other is a negative surface. Positive surface is one on which the outer normal points towards a positive x axis, whereas the negative surface has its outer normal pointing in the negative x direction. On a positive surface, a vertically upward shear force is a positive shear force, whereas on a negative surface, a vertically downward shear force is a positive shear force. So, two positives or two negatives make a positive shear force. However, if the surface is positive, but the shear force is downward, then it is a negative shear force, and similarly on a negative surface an upward force will be a negative shear force. Similar nomenclature is applicable for bending moments. On a positive surface, an anti-clockwise moment will be a positive bending moment, whereas on a negative surface a clockwise moment will be a positive bending moment. And similarly, on a positive surface, a clockwise moment, that is a negative moment, is a negative bending moment, and we can say for the negative surface an anti-clockwise moment will produce a negative bending moment. So, again remember, two positives and two negatives make a positive bending moment, one positive and one negative makes a negative bending moment. So, let us continue our discussion from this point onward. Now, in the design of beams, which you will be learning in later courses like solid mechanics or strength of materials, there are two important considerations. One is the maximum bending moment and the other is maximum shear force, because the size or the shape of the cross section of the beam is very much dependent upon these two parameters. So, it is very important for a designer to find out what is the magnitude of the maximum bending moment and where it occurs. Similarly, what is the magnitude of the maximum shear force and where does it occur. In order to determine this or to get this information, we must calculate or graphically display bending moment at every section as well as shear force at every section. A graphical display of this information is called a bending moment diagram or shear force diagram Well, the diagram which depicts bending moments is the bending moment diagram, etc. Let us start with the procedure to obtain or to draw these diagrams. Now, for this we will study the equilibrium of an arbitrary beam loaded by transverse load. There are two types of analysis which are available, which are useful. One is for distributed loads, the other is for concentrated loads. Let us start with the case when the load is distributed along the length of the beam. The distribution function is very well defined. Let us say Wx is the load per unit length of the beam, and its units will be Newton per meter. Okay. Vx is the shear force distribution from section to section as a function of x, and similarly Mx is the bending moment at any section x. This is shown over here. This is the beam, xy coordinates are shown, z is perpendicular to the plane of the screen, and this is an arbitrary loading function Wx. Let us focus our attention on a small segment of the beam whose length is delta x, a very small element. Okay. Blowing up that section, that segment of width delta x, and Wx is the loading on this. Remember, on the right hand surface the outer normal is in the positive x direction, outer normal is drawn like this. So, it is a positive surface, and accordingly the left hand section is the negative surface. On a positive surface we have a positive shear force Vx going upward, and similarly on a negative surface we have a downward shear force which will be positive. Now, let us say on this surface, if Vx is the shear force, then since the shear force is varying along the length of the beam, on a surface which is at a distance delta x from this surface, let the shear force be Vx plus its variation delta Vx. Okay. Similarly, Mx, the bending moment on a negative surface, clockwise moment will be a positive bending moment, and on a positive surface you have Mx plus its variation over length delta x, that is delta Mx. So, now this segment of the beam of width delta x is in equilibrium, because the entire beam is in equilibrium. Hence, any internal free body, whether it is a small segment or a large segment, should also be in equilibrium. So, we focus our attention on this segment loaded with a direct load, and on the faces you have bending moment and shear force. Writing down the equations of equilibrium for this free body: sum of all the vertical forces, that is sigma Fy is equal to 0. So, this is the Wx delta x is the load, going back to the figure. This is the Wx is the load per unit length, and delta x being the length, because it is a very, very small length. So, you can consider it to be an average load times delta x. So, that is the total load on this segment. Then this is vertically downward, vertically upward loads are Vx plus dVx, and downward load is again Vx. So, looking at this equation, minus Wx dx downward load plus Vx plus dV upward minus Vx downward. So, this is equal to 0. Now, Vx and Vx will cancel out. You can easily see if I divide both sides by delta x, so dV delta V by delta x is equal to Wx, and since the segment is infinitesimally small, so delta x, as delta x goes to 0, this quotient becomes the derivative. So, dV by dx is equal to Wx. So, this is the equation number 1, which relates the slope of the variation of shear force with the distributed load Wx. So, dV by dx is equal to Wx. Now, again carrying out the free body analysis, the sum of the moments must also be equal to 0. So, sigma mz is equal to 0. So, again going back to the figure, what are the moments applicable? There is a moment of mx which is clockwise, and anti-clockwise moment of mx plus dmx. So, you will have m plus delta m minus m. Okay. Now, this is the moment due to the shear force Vx into delta x, and this is the moment due to the applied load Wx. So, these 4 terms, when they are simplified, m and m will cancel out, and when delta x goes to 0, it becomes very small. See, the remaining terms are first order infinitesimal, that is, they have a delta x only once, but the last term has 2 delta x. So, it is proportional to delta x square. So, it is a second order infinitesimal. So, in the limit, this term will contribute very small, and hence we neglect it. So, dm by dx is equal to minus Vx. So, this means that the slope of the variation of bending moment dm by dx is equal to the shear force with a negative sign. Okay. So, equation 1 and 2 give us the relationship between the loading function, shear force distribution, bending moment distribution. We can integrate these 2 equations to get the shear force function and the bending moment function. Okay. So, from the equation number 1, that is from here, you can integrate it and you get the equation number 3, that is Vx or x prime is obtained by integration of Wx, that is the dV by dx, okay, and this is the constant of integration. And secondly, you integrate this once again to get, because the derivative of bending moment is equal to negative of the shear force. So, from here you can find out mx is equal to negative minus. So, this is Vx. So, once we integrate it, so then C will be also integrated to get Cx, and d is the constant of a second integration. So, this is the expression for the bending moment in terms of the load distribution function Wx, and this is the expression for the shear force in terms of the load distribution function Wx, and C and D are 2 constants of integration which must be determined from the boundary conditions. So, to summarize, when the loading on a beam is given by a well defined function, it may be a constant function or a linear function or a sine function or an exponential function, any well defined function, then through differentiation and integration we can get the bending moment distribution as well as the shear force distribution, all analytic functions. To illustrate this procedure, let us consider a very simple example. Suppose there is a beam of length L, incidentally this is called the span of the beam. L is, so we will say a beam of span L meters, and it is supported at two ends. At one end there is a simple support or a pin joint where theoretically both vertical and horizontal reactions are possible. At the other end it is a roller support, that is only vertical reaction is possible. So, the total number of reactions which can be solved for are 3 in general, although in this case loading is only vertical. So, there is no horizontal reaction, and 3 reactions can be determined from 3 equations of equilibrium considering the entire beam as a single free body. So, number of equations is 3, unknown is 3, so it is a statically determinate problem. So, this problem is statically determinate. Now, we want to determine for this problem the bending moment diagram as well as shear force diagram. First, we will determine the analytic functions and then we will plot the diagrams. Well, going back to the picture, you can see that everything is uniform, loading is uniform, geometry is uniform, and there are only vertical reactions. So, the problem is a symmetric problem. If I consider that through the middle section of the beam there is a mirror, then the right hand and then the left hand beam and loading is a mirror image of the right hand beam and the corresponding load. So, whenever you have a symmetric problem, then automatically the reactions will also be symmetric, that is R A and R B both are equal. Okay. You can do it otherwise also by considering sigma Fi is equal to 0 and sigma Mz is equal to 0. Let us say if I take the moment about B, then you will get R A easily, and similarly if I take the moment about A, then you will get R B easily. So, by symmetry of loading and as well as the beam, R A is equal to R B, total load on the beam is W0 L, W0 being the load per unit length. So, and L is the length of the beam. So, total load is W0 L, and hence each of the reactions will be equal to half of it. And now, since the loading function is a constant function W0, it is independent of x. Okay. So, you can substitute into the equations which we derived earlier, mx, if I substitute for this W0, then integrate it and we will see that we will get this simple equation, mx, the bending moment at any function at any section x is equal to minus W0 x square by 2 parabolic minus you can have plus Cx plus d. Okay. C and d are to be determined from the boundary conditions. What are the boundary conditions? Both ends are simply supported, they cannot sustain any rotation. So, any moment, therefore, the moment at x is equal to 0 as well as x is equal to L has to be equal to 0, because if there is a non-zero moment, it will cause the rigid body rotation of the beam. So, it means that first I put x is equal to 0, this term will be 0, this term will be 0. So, d must be equal to 0. Okay. And then I put x is equal to L. So, that will determine again m at L is equal to 0, d is already found out to be 0. So, this term will be minus W0 L square by 2 and this term will be equal to CL. So, you can easily see that C will come out to be minus W0 L by 2. This is the expression. So, substituting back these values of D and C, we will we can easily know that the variation of the bending moment, that is function mx, is equal to minus w0 into x by 2 into x minus L in the brackets. And once if we differentiate it once with the negative sign, we will get the shear force, and in doing so we will get the shear force Vx is equal to W0 by 2 into 2x minus L. Okay. As a check, when we put V is equal to 0 and at x is equal to 0 and x is equal to L, we will get the shear force as W minus W0 over L by 2 and W into L by W0 into L plus W0 into L by 2. So, these are precisely the two end reactions. Okay. So, it means our analysis is proceeding on the correct lines. And if I plot this, well, at the end A, the shear force is equal to negative of W0 L by 2. So, minus W0 L by 2. So, and the function is shear force function is a linear function. You can easily see here is a linear function. So, it means it varies in a straight line, and at the end B the same shear force is positive. So, very easily drawn the straight line distribution of the shear force. And secondly, when we plot the bending moment, we have seen that at both the ends the bending moment is 0. So, it starts from 0, you can see that bending moment is 0 at both these ends. So, and this term will be x square by 2 and this will be, so there will be a parabolic term. So, the function will be the shape of the bending moment diagram will be parabolic. So, between A and B, this is the parabola, and the maximum shear force bending moment occurs, well, you can see as I mentioned, for maximum or minimum the dm by dx has to be equal to 0, and at that point the shear force must be 0, because dm by dx is equal to minus Vx. So, it means since the shear force is 0 at the center of the beam, it means the maximum bending moment will also occur at the center of the beam. So, this can be easily verified. This is occurring at the center of the beam at x is equal to L by 2. So, its value at that point is W0 L square by 8. So, for well defined loading functions, we can quickly and very simply get the bending moment and shear force diagrams, and they are consistent with the end conditions. Next, I will take up one more example. Here the loading is a triangular loading, that is, there is a 0 loading at one end and gradually rises to a maximum low loading of W0, which is load per unit length, Newton per meter. So, this is the loading rate. Okay. So, you can imagine that on this beam a triangular wall has been built. So, as the height of the wall is increasing, load is also increasing. So, in this way you can visualize this problem. Again, one end is simply supported, the other end is roller supported. No horizontal load, no reactions are possible, and no horizontal reactions are needed. So, only vertical reactions will be needed. Now, to analyze this problem, you can replace this triangular load by equivalent loading. You have learnt in chapter 3, in lecture 3 and 4, how to replace a given loading by its equivalent loading. So, for a triangular load, we can find out the total load, that will be the area under this triangle, the area under the triangle will be base times altitude divided by 2. So, W0 into L by 2, that is the total load. And where does it act through? It will be acting through the center of gravity of the triangle, that is centroid of the triangle, and this occurs at somewhere here along a line which divides the total span into two parts, 2L by 3 and L by 3, as I am showing in the next slide. The total triangular load is replaced by a single concentrated load W0 L by 2, which is area under the triangle, and its location is such that the span is divided into two parts, 2L by 3 and L by 3. Okay? And if you consider this entire beam with this loading as a free body, then you can find the reactions from the equilibrium equation. I will not do it now, you can do it yourself. It is by simply taking this summation of vertical forces is equal to 0 and summation of the moments about any point A or B, both points are equally good. You can find out one reaction at A will be W0 into L by 6, the other reaction at B is a W0 L by 3. So, having obtained these two reactions, now again we go back to the analytic solution, load distribution function. Now, well, once again it is a triangular function, okay, linear function. So, it means it will vary from 0 to maximum of W0. So, you can easily see that this will be equal to the load distribution function will be W0 x divided by L. So, W0 x divided by L. Now, the formulas which we have already derived connecting mx, that is the bending moment distribution, with the loading distribution. So, this is direct substitution of the formula. So, the loading function Wx is replaced by W0 x divided by L. So, and you integrate it once, twice, you will, and then since both these supports are simple supports, so the bending moments at these two supports must be equal to 0. So, m at x is equal to 0 is 0, which will give this constant of integration d is equal to 0. M at x is equal to L is equal to 0. This gives easily the constant of integration as W0 L by 6. Okay. And once we have obtained these two constants, I substitute back into this equation to get the final expression for bending moment. Mx is equal to minus W0 x taken common outside into x square minus L square whole divided by 6L. So, this is the expression for the bending moment. And once I take the derivative of this bending moment and put a negative sign, I get the shear force. So, substituting back, we will get Vx is equal to W0 into 3x square minus L square whole divided by 6L. So, both bending moment and shear force have been obtained as analytic functions, and rest we have to only plot them. Well, let us first plot the shear force. At x is equal to 0, you will easily get W0 minus L square divided by 6L. So, W0 L by 6 with a negative sign. So, this is when x is equal to L, you will get W0 L by 3, and as a check that our procedure has given correct results, these are precisely the two reactions. Okay. So, this is a parabolic equation. So, you join these two endpoints with a smooth parabola, and it will intersect the x axis at this point. Okay. This is the point where shear force is 0. What does it imply? The bending moment at precisely this point will be maximum. And when we plot the bending moment diagrams, here will be a cubic parabola. Here is x and x square term, so it means it is a x cube term, it is a cubic parabola. And again at both the extremities at point A and B, the bending moment is 0. So, we get a cubic parabola, and then after it goes through the maximum, it falls again. And the maximum value you can determine from the previous expression. You can determine at that point where the shear force is 0. This is 0 at x over L equal to 1 by root 3. So, at x is equal to L by root 3 or L divided by 1.731 or something like that. So, the maximum bending moment occurs and its value is given over here. So, through these two examples, we have seen that when we have well defined loading functions, we can easily get both the bending moment distribution and shear force distribution. And one conclusion was very important: when the shear force is 0, the bending moment is maximum or minimum. Okay. Now, the second type of analysis for bending moment and shear force is needed when the loading is concentrated. The load function may be itself concentrated, that is at a point a non-zero load is being applied, that is over a almost zero length you have a non-zero load, and similarly at a point there may be a non-zero moment applied due to some twisting or due to some brackets, as we will see. The problem with this concentrated load or moment is that they cannot be defined by regular functions. They need singular functions, and the mathematical analysis, although it can be taken up, but it becomes very complicated. So, it needs functions like Dirac delta functions, Heaviside function, etc., which we will not be covering in this course. But there is a simpler procedure which can be resorted to whenever you have concentrated force or concentrated moment applied to a beam. And what is that procedure? We will, wherever there is a concentrated load, we will separate that section. Okay? So that at that point we will first consider a section to the left and then section to the right, and we will proceed from section to section and cover the entire beam. So, in this manner, I think the best way is to illustrate this procedure with the help of an example. Here is an example. A simply supported beam is loaded, beam is AB, it is loaded by a concentrated load of 2 kilonewtons at point C, and there is a bracket at 90 degree, which is at 0.5 meters offset from the axis of the beam, and this bracket is being pulled with a force of 4 kilonewtons. So, now this is quite obvious, this is a singular force, and here if I consider the free body of this bracket, so it means that, suppose I show it over here, this is the bracket, this is a force of 4 kilonewtons, and there will be equal, to maintain this in equilibrium, there will be an equal and opposite force of 4 kilonewtons, and also there, due to these two there will be a couple. So, the couple has to be maintained. So, there will be a, so now the bracket is in equilibrium, and at this junction between the bracket and the beam there will be equal and opposite reaction. It means at that point D there will be a horizontal force of 4 kilonewton towards right, and there will be a clockwise moment at D of 4 into momentum being 0.5, 2 kilonewton meters. Okay. So, if I show it over here, so this beam with the bracket is simplified as a beam with a concentrated load of 2 kilonewton at C. At D there is a couple whose moment is 2 kilonewton meters, and R A and R B are the two reactions. First part is you can determine the reactions by considering the entire beam as a single free body. R A plus R B is equal to 2 kilonewtons, because sum of the vertical forces is equal to 0, and similarly take moments about either point A or point B. Here I have taken it about point B, and you from this equation taking moments about let us say total length is 6 meters. So, 6 into R A, which is clockwise, hence negative, plus 4 into 2. So, 2 kilonewtons into 4 anticlockwise positive, and then there is a negative moment due to couple of 2 kilonewton meter equal to 0. So, R A comes out to be 1 kilonewton, R B also 1 kilonewton. So, overall equilibrium gives us the two reactions. Now, I will consider in this case 3 sections. One section anywhere between, this is our x direction and this is our y direction. Okay. So, at from x is equal to 0 to x is equal to 2 meters, then the second will be between C and D, that is x must lie from 2 meters to 4 meters. Then the third section will be from D to B, this is B, this is A. Okay. So, D to B means x going from 4 to 6. So, we will proceed from section to section. Let us do that. First section anywhere between 0 to 2. Consider the section between x is equal to 0 or slightly more than 0, because here is singularity here. So, 2 x is equal to or less than 2. So, in the first section. So, let us note down all the forces. There is a reaction R A which was determined as 1 kilonewton, and there is a moment M, and the shear force on this section on the positive surface, a positive upward shear force of V. Okay. So, V and so this consider there is no other loading. So, consider the equilibrium of this part of the beam. So, sum of the vertical forces R A plus V both upward equal to 0. So, it gives us V is equal to minus R A, and which is equal to 1 kilonewton. So, it means in this section the shear force is a constant value of minus 1 kilonewton, and then you take the moment about let us say the middle of this section. So, this first R A will give you clockwise moment which is negative. So, R A into momentum is x. So, R A into x plus m equal to 0. So, m is equal to R A x is equal to, since R is 1 kilonewton. So, it is simply R A m is equal to x kilonewton meters. Okay. And this is a linear function. Next we go to the section anywhere between x greater than or equal to x less than equal to 4. So, in that section you can easily see I am considering a section over here, okay, any section here, for example here or here. So, the consideration will be what are the forces R A, downward force of 2 kilonewton, and similarly V and M. So, again sigma F y is equal to 0, sigma M is equal to 0, etc. So, V plus R A minus 2 is equal to 0, and hence V gives us 2 minus R A, which is R A is 1 kilonewton. So, simply plus 1 kilonewton, and M will be equal to 4 minus x kilonewton meter. And then we come to the third section between D and B, okay. And at D there is a concentrated moment due to bracket, remember. So, we have a concentrated moment of 2 kilonewton meters, and you have these one force, one moment, and the end force due to reaction. Again sigma Fi is equal to 0, sigma mz is equal to 0, and these two equations are obtained. Now, the only thing to do is we have to depict these results graphically. Let us do that. This is the beam as given to you, R A and R B, two reactions which are both found to be 1 kilonewton each, and then applied load of 2 kilonewton, applied moment of 2 kilonewton meters. All right. So, this is the shear force diagram SFD, and this is the bending moment diagram BMD, and this is the loading diagram. Okay. And you can see that wherever there is a concentrated load or a moment or end reactions, I have drawn vertical line just to indicate the sections. Here you have first between 0 and 2, if you look at the equations, what two equations we had between 0 and 2, 1 kilonewton negative and a linear function x. Okay. So, 1 kilonewton negative, which was constant in that section, and a linear function for bending moment. And then at this point of C, there is a concentrated load of 2 kilonewton. So, there will be a jump at the indicating 2 kilonewton. So, 1 kilonewton, 1 kilonewton. So, this discontinuity amounts to 2 kilonewton, and after that there is no loading here, only there is moment. So, the shear force will be constant, and here it is equal to the reaction at B, which is positive 1 kilonewton. So, you see that wherever there is a concentrated load, there is a jump in the shear force diagram. A concentrated moment will not produce any change in the shear force. On the other hand, where we had a concentrated moment, there is a jump in the bending moment. So, well, this is again linear. If you see in the second section, again it is a linear function, and in the next section again it is a linear function. So, it consists of 3 linear functions. Bending moment diagram consists of 3 linear functions and 1 jump. So, this is exactly what we get. 3 linear functions, 1, 2, 3, all parallel, slope is same, and this is the jump. Okay. So, where the shear force was going through 0 over here, and it is consistent with our results that bending moment is maximum when the shear force is going through 0. So, everything is tying up very well. So, this is how you will plot a bending moment and shear force diagram when the loadings are concentrated. Let me take up a very interesting problem with the mixed type of loadings. On some part of the beam there is a distributed load, a well defined uniform function, okay, or as it is something called rectangular loading, uniformly distributed load or rectangular load, and there is a concentrated moment and a concentrated load. Now, this beam is having double overhangs, that is, towards the left of the support C, it is the beam is loaded, and towards the right also of support E there is a load. So, these two portions on either side of the supports, they are called overhangs. So, now first we will consider the entire beam as a single free body to determine the two reactions, and then we will proceed from section to section. There will be one section from A to C, second section C to D, third section D to E, and the last section E to B. Now, I will not go through the same section wise analysis, because once you get enough practice, you can almost do the analysis just by looking at the beam and the type of loading, okay? Because you expect when there is a, we have done already a problem, analytic problem, when the loading was a uniform loading. We saw in that case the shear force diagram was a linear function and the bending moment was a quadratic function. So, you can expect similar thing to happen from A to C. There will be a shear force which is linearly varying and a bending moment which will be quadratically or parabolically varying. Between C and D there is no load. So, the influence of this uniform loading will be there. You can replace it by this uniform load by a single equivalent load at the middle of the rectangle, and then you can determine again the shear force and bending moment. Or you can also proceed from the end B. Okay. So, again due to single concentrated load, you will find that the bending the shear force will be a constant function and the bending moment will be a linear function. So, if you remember these simple results, you can do the bending moment shear force diagrams analysis very quickly. Let us do it. Well, from reactions, considering the entire beam as a single free body, R1 plus R2 is equal to a load of 10 kilonewtons on the overhang and a uniform load 2 into 5, that is 10 kilonewtons here. So, 10 plus 10, 20. So, you can see that you have 20 kilonewtons and take the moments about the point C, that is where reaction R1 is acting. So, you can quickly see that your R2, the reaction at the other end, is obtained as 9 kilonewtons and R1 will be 11 kilonewtons, because their sum is 20 kilonewtons. So, by these two equations of equilibrium, two reactions R1 and R2 are determined. Next we will see, as I indicated, in the first partial overhang, that is from A to C, there is a uniform loading and the shear force will be linearly varying, that is, it is equal to 2 kilonewtons times x. Okay. So, it is a straight line function. So, and this will be a quadratic function, that is starting from 0, because the this is a unsupported free end. So, no moment can be sustained there. So, starting from 0, it is increasing parabolically, and the value can be obtained again. You replace it by the total load of 10, 5 into 2, that is 10 kilonewton at the center. So, you can say that this is equivalent load of 10 kilonewtons, and this will produce 10 into 2.5, that is 25 kilonewton meters. So, this will be the bending moment at the point C. And now, if I proceed from, because that will be very easy, proceeding from the end B. So, again there is a load of 10 kilonewton over here, and that will give me a constant shear force, because there is nothing, no loading in between E and B. So, that will be a 10 kilonewton shear force, and this will be the corresponding this is 10 kilonewton times the distance here. So, it is gradually rising, and at point D you can see there is a concentrated moment. So, I can expect a jump in bending moment here. At C there is a concentrated reaction. So, there is a jump in the shear force diagram here, a jump in the shear force diagram here, a jump in the bending moment diagram here, which are all satisfied by looking over here. There is a jump, there is a jump, there is a jump. Okay. So, you can recapitulate all the features of the bending moment shear force diagram without going through the total analysis. Mind you, you should be able to have enough practice to do that. Otherwise, we can proceed in the usual way, that is, we will first consider a section between A and C, consider its free body diagram, calculate the value of V and M. Then you consider a section between C and D, again you can draw, you can consider the free body which will have this load, reaction here, and a shear force and bending moment on the cross section. Write down the equations of equilibrium, and in this manner you proceeded. The third section will be over here, fourth will be in this part of the beam. So, if you proceed from section to section and analyze each of the internal free bodies, you can derive those equations for bending moment and shear force, and then you plot them. Or by looking at it, by recognizing what should be the variation, linear, quadratic, cubic, etc., you can get some idea, and wherever there is a concentrated load, whether it is a applied load or a reaction, you will see a discontinuity or a jump in the shear force. Wherever there is a concentrated moment, you should see a jump in the bending moment diagram. So, these are some of the automatic checks for you. And finally, wherever the shear force goes through 0, you can expect a maximum, a local maximum or minimum in the bending moment. All these features, for example, here it goes through a maximum over here. So, shear force is 0 at point E, you can see it. So, the bending moment is going through a maximum over here. So, to summarize, we have seen that beams which constitute very important structural members, load bearing members, they need the information about the distribution of bending moment and shear force for designing them. And this information can be obtained by plotting the bending moment and shear force diagrams. wherever the bending moment is maximum, that is the point where the stresses, as you will be learning later on, will be maximum, and accordingly the beam has to be designed on the basis of the maximum bending moment. And also again when the shear force is maximum, again for certain types of beams that information is very much needed, particularly flanged beams with webs, etc. Okay. So, in our next lectures we will start with further analysis in mechanics, namely friction. Thank you very much for your attention.